Darrieus turbines have one of the most complex dynamic stall-inducing motions in the world of man-made machines, simply by virtue of their design. Here is an animation of a single-bladed Darrieus turbine viewed from the top. The blade begins at the 12 o'clock position, aka at 0 degrees theta, and rotates counterclockwise around the central axis. Did you notice something? Let's rewind. Notice that the blade is actually pitching as it rotates about the axis. At 0 degrees theta, the leading edge is facing the inflow. At the 6 o'clock position, aka 180 degrees theta, the leading edge is facing away from the inflow, which means the airfoil has pitched by 180 degrees. By the time the airfoil completes one revolution, the airfoil leading edge is once again facing the inflow, having pitched 360 degrees. The pitch rate and amplitude are huge factors which affect dynamic stall. The next thing to notice is that at the 0 degrees theta position, the blade begins to plunge downwards with an amplitude equal to the diameter of the rotor. It goes down and goes right back up by the end of the cycle. The plunging amplitude and plunging rate are also huge factors which affect dynamic stall. But you think that's all? Not quite. If you had noticed the plot on the bottom left, this is a plot of the instantaneous blade Reynolds number against the blade's azimuthal location. The red dot follows the rotation of the blade in the animation as it rotates about the central axis. Observe how the instantaneous Reynolds number is changing all the time. In fact, the Reynolds number is lowest at 180 degrees theta and highest at 0 degrees theta. These three factors, pitching, plunging, and changing instantaneous Reynolds numbers, are working in tandem. So you can see why the effects of dynamic stalls on Darrieus turbines is still such a mystery. I actually also have an announcement for you guys. Be sure to stick around all the way to the end of this video because that's where I'm going to be telling you where you can get your free gift from. And now coming back to the video. I'm going to put an end to this debate once and for all. It took me 1.5 years to thoroughly understand the effects of dynamic stalls on Darrieus turbines. And trust me, this stuff is not one bit easy because there's so much confusion in the literature about its effects. And there are papers that merely mention how dynamic stall is bad without elaborating on why. They simply did not produce any demonstrable evidence that dynamic stalls is bad for Darrieus turbines. And now I'm taking all of my experience and knowledge and putting it into a video specifically for you guys because I know how painful it is to go through this. Understanding unsteady aerodynamics, specifically dynamic stall, on Darrieus turbines is crucial, especially if you're serious about studying these types of turbines. Let me begin by saying that dynamic stalls on Darrieus turbines occur because there are excursions of the angle of attack beyond the static stall angle. And these excursions exist because the angle of attack of the blades are always changing. Here is a plot of how the angle of attack varies with the azimuthal location and tip speed ratios. The left-hand axis is the angle of attack, the bottom axis is the azimuthal angle, and the various lines on the plot represent different tip speed ratios. For the tip speed ratios of about between 0 and 1.5, you can clearly observe that as the blade starts at 0 and rotates about the axis, the angle of attack extends beyond plus minus 60 degrees, really high. But notice that as the tip speed ratio increases, the angle of attack range decreases. By the time we hit a tip speed ratio of about 4, the angle of attack ranges from about 0 to plus minus 10. An angle of attack of 10 is still smaller than a static stall angle for most airfoils. If the angle of attack never exceeds the static stall angle, then dynamic stall never happens. But if it does exceed the static stall angle, then dynamic stall happens. So in this scenario, for most Darrieus turbines, dynamic stalls tend to occur only between the tip speed ratios of about 0 and 3. But what exactly are dynamic stalls on Darrieus turbines? For regular airfoil stall, we are always concerned with steady flows and a steady airfoil. When the angle of attack shifts such that it now exceeds the stall angle, the flow becomes detached from the airfoil, and the airfoil immediately experiences stall and the lift magnitude plunges drastically. But for dynamic stall, the fundamental difference is that the airfoil or the inflow itself is unsteady. When either the airfoil or inflow is unsteady, and when there are excursions of the angle of attack beyond the static stall angle, that's when the magic happens. That is, the airfoil does not immediately experience stall, and the lift magnitude continues to rise. Let's use the single-bladed Darrieus turbine as a way to explain what happens. This is what I call a turbine vector diagram, which is a free body diagram of a single-bladed Darrieus turbine. The airfoil and its lift, drag, thrust, and angle of attack vectors are plotted automatically using a software I developed called Drafa. Drafa is a tool specially built to analyze Darrieus turbines and takes you from data to insights in just a few seconds. Taking the time to develop it was probably one of the smarter things I've done. It's saving so much of my time right now and it's paying huge dividends. Let's say that the blade is at the 0 degrees theta position and the angle of attack is more or less -4 degrees. The angle between the relative velocity vector and the airfoil chord represents the angle of attack. As the blade rotates about the axis, this angle begins to increase. Just after the angle of attack exceeds the stall angle of attack, the flow is still attached to the airfoil, albeit a slight bout of reverse flow begins to form at the trailing edge. Again, this phenomena is in contrast to that of a steady airfoil, where immediately after exceeding the stall angle of attack, the flow detaches and the lift magnitude drops tremendously.
They ask you how you are, and you just have to say that you're fine when you're not really fine, but you just can't get into it because they would never understand.
But not in our dynamic stall scenario. As the blade continues its rotation, the angle of attack increases, yet the flow is still attached. Over time, as the angle increases, the separation point, that is, the point at which the flow detaches at the trailing edge, moves upstream towards the leading edge. Eventually, one big dynamic stall vortex forms, and it begins to translate down the surface of the airfoil. Miraculously, during this entire process, the lift continues to rise despite operating well beyond the static stall angle, undoubtedly due to the effects of the dynamic stall vortex on the pressure distribution around the airfoil. Lift is enhanced and can be enhanced by a humongous amount, think 200 to 300%, while the drag is only increased marginally, perhaps by about 10 to 15% or so. As the blade continues its rotation, the angle of attack continues to rise, and the dynamic stall vortex eventually detaches from the blade, and all hell breaks loose. A detached flow regime immediately forms behind the blade, and the lift drops instantly. As the blade continues its rotation around the axis, it struggles to regain attached flow behavior. Even if the angle of attack reduces to below the static stall angle, the flow is still detached temporarily. In this regime of performance, because the dynamic stall vortex detachment caused a massive dip in lift, we can expect the Darrieus turbine to perform poorly. But many are still confused as to whether the positive effects of dynamic stalls outweigh the negative effects of dynamic stalls. I'll give you guys the answer straight away. The answer is that it is actually a net positive. Several studies have come out analyzing the true effects of dynamic stalls on Darrieus turbines, including ours, where we analyzed the effects of dynamic stalls on self-starting Darrieus turbines and published in Physics of Fluids. I simulated a Darrieus rotor from rest to its nominal tip-speed ratio using an open-source software called QBlade. QBlade is a low to medium fidelity turbine analysis software that uses either the blade element momentum model or the lifting line free vortex wake algorithm to accurately simulate the behavior of a turbine. QBlade gets you legitimate results with relatively low computational costs. Lastly, no, they're not sponsoring this video. I just really like their tool. If you want to simulate turbines very quickly and accurately, you should check them out. My work shows that two dynamic stalls tend to occur in these 4 quadrants. The first will either be in the windward or in the upwind quadrants, and the second will happen in the leeward quadrant. With regards to the first dynamic stall, its location depends on the tip-speed ratio. At lower tip-speed ratios of about between 0 to 2, the dynamic stall tends to happen in the windward quadrant, and at higher tip-speed ratios of about between 2 to 3, the dynamic stall tends to happen in the upwind quadrant. It really depends. Here is a plot of the thrust coefficient of the airfoil as it rotates 360 degrees about the central axis. The left-hand axis represents the magnitude, and the bottom axis represents the blade's angle of attack. You may refer to the animation on the right when it starts to play to correlate the angle of attack shown in the plot right here with the current azimuthal location. You read the plot by beginning here, following these 2 dots. The dark solid line represents the dynamic thrust coefficient, that is, the thrust coefficient recorded as the blade rotates about the axis. The dashed line, however, represents the steady thrust coefficient. That is, it's obtained by quasi-statically rotating the blade about the central axis. What do I mean by that? Simple. At an arbitrary azimuthal location, say about 25 degrees theta, we know the angle of attack. It can be approximated by this formula shown on the screen. Therefore, using available polar data online, we automatically know the lift and drag magnitudes. From these three variables, we can compute the thrust. We then manually rotate the airfoil forward by, say, 2 degrees theta. This will be our step size. At this new azimuthal location, again, we know the angle of attack, we know the lift, and we know the drag coefficients. Therefore, we can compute the thrust coefficient, and on and on and on. The main point of this plot is to isolate the effects of unsteady aerodynamics, or more specifically, dynamic stall. It allows you, the user, to really understand which regions are enhanced or are negatively affected by dynamic stalls. I'm quite certain that if you're studying dynamic stalls on Darrieus turbines, you'd eventually need to have this kind of plot. I've developed a special software module embedded inside Java to help me compute this static thrust coefficient. It took me just a few seconds to come up with these plots. One tricky thing about computing this static thrust coefficient is that the instantaneous blade Reynolds numbers are changing all the time, which means that the polar data you need to use will change at every single time step. I've validated the algorithm many times over, and the results that came out of the algorithm were eventually published in Physics of Fluids, so it's pretty legit. Coming back to the comparison between the dynamic and the static thrust coefficient, you can clearly observe in the dynamic stall regions here that the dynamic thrust coefficient is typically always larger than the static thrust coefficient. Only in some locations is the dynamic thrust coefficient smaller, and these regions tend to be the regions where the dynamic stall vortex has detached. In fact, if we were to take the average dynamic thrust coefficient and compare it to that of the average static thrust coefficient, we will find that the average dynamic thrust coefficient is positive, very positive in fact, while the average static thrust coefficient value is negative. If a turbine blade has a negative thrust coefficient, it better have other blades to help make up for it. In this scenario of a single-bladed Darrieus turbine with a negative thrust coefficient per cycle, you can bet that this turbine is going to slow down. Therefore, according to the mean thrust coefficient values, it's pretty clear that dynamic stall is actually a requirement for the turbine blade to generate positive torque, and therefore to accelerate the turbine. So there you have it, the effects of dynamic stalls on Darrieus turbines. It's definitely a net positive. If we can find a way to abuse dynamic stalls on Darrieus turbines, active pitching, in theory we should be able to massively boost and amplify the amount of torque generated per blade, and therefore push the Darrieus turbine to even higher tip speed ratios and therefore generate more power. Earlier I mentioned to you guys that I have a surprise for you. I've actually put together a comprehensive package on how to analyze Darrieus turbines. Stop struggling with understanding, start getting actionable insights immediately. Cut through all the noise. You don't need to read 1 million billion papers to finally understand how to start analyzing your turbine aerodynamics. Most importantly, relieve yourself of the uncertainty in researching Darrieus turbines. Click the link in the description below to get your free copy. By the way, if you're interested in using any of my free software or algorithms, of course you can. But first, I'd like to know what you want to use it for, and maybe perhaps I can see if I can help you in any capacity beyond just giving you the software and the turbine aerodynamics analysis PDF guide. You can schedule a one-on-one call with me down in the link below, and we can meet up and I can give you the software. Thank you guys for watching. Take care.